How are you all this afternoon? How's the projects and assignments coming along? Good, good. Have you managed to finish the assignment yet, or still working your way through? Okay, that's good. It's due in week 14, so you still got plenty of time. This week's tutorial, I'll be covering the assignment. So if you have any questions about any of the steps or any of the different analysis types that we have, please let me know and I can focus on those specific steps. Okay. So do you have any specific problems anywhere along the way with the analysis? Greg, welcome to the session. I saw your message in the 101 pass group. Just wondering, are you finding everything okay? Any questions about the assignment? For you guys who didn't manage to submit your assignment your tutorial activity last week, yes, you can still update them, put them in the Viber group chat, and I'll update your attendance for either of the last 2 weeks, week 10 or week 11. All right, if you don't have any specific problems or issues with the assignment, then I'll just start very broad and then briefly cover maybe the more difficult ones like the bolt analysis or the hub analysis. All right, those two may be a little bit difficult. We can cover those two. Okay, before we begin, this assignment, we are looking at using engineering terms, engineering theory, to help design a part. And the part that we have to design is a flange coupling, which has to transfer power from one shaft to another shaft. Right, and when we transfer that power, we want to make sure that it's 100% effective. What I mean is all of the power produced in shaft A is going to be transferred to shaft B. That's the ideal goal, that's the ultimate goal of this part. But of course, in that transference, there will be forces generated, and we have to make sure that our coupling is able to withstand those forces without breaking or failing. So before we begin, just a quick recap. Can anybody tell me the types of forces that you might come across? There are lots of different types of forces, but specifically aimed at engineering, what are maybe 4 of the most common types of forces we come across? Any ideas? So if you're taking civil or mechanical engineering, this assignment is pretty much the grassroots, the base, where it all begins for you. Because from this point on, the concepts that you apply in this assignment will be elaborated on more and more as you go through the years. Yes, Sanya, the first one is tension. Tension or tensile? Tensile force. Any others? Any other forces you think? The opposite to tension, compression. Compression or compressive. Another one. Torsion. Torsion is a function of force. So torsion is force times distance. So the torsion will create the force, but it's not a type of force. If you get what I mean. Yes, Elizabeth. The other one is shear. And just one more. This one here, we're not looking at in this assignment, but it's just important to know that it's another force, sorry. And we have briefly touched on it in one of our lectures, one of our tutorials in earlier weeks, and that is friction. Now for this assignment, we don't have to worry about friction because we don't have any parts that are moving against each other. So if like parts were like rubbing each other, or, you know, our coupling had to slide along the shaft, then we would look at friction. But this assignment, we don't have to worry about friction. We're going to look at tension, compression, and shear. Right. So what does a tensile force look like? Let's say we have a cylinder of some kind of metal. This is an area A, and we have a force acting in this direction, pulling this piece of metal. This is a what type of force? Yes, this is a tensile force. Tensile force. It's pulling the piece of metal apart. Technically, a tensile force is a force that is acting away perpendicular from the area. So when it's acting perpendicular to the area and it's pulling the member, that's a tensile. And opposite, if it's pushing or compressing the element, this is a compressive force. And the other one, so the tensile and compressive forces both act perpendicular to the surface. So these are normally termed as normal forces. Shear is the odd one out. So if we look at this element again, and we have a force acting in this direction on this area A, and it's acting parallel to the surface and causing the surface to want to slide or slice, this is a shear force. Okay, so tensile and compressive, they act perpendicular to the surface, and the shear force acts parallel to the surface. So in this assignment, we'll be looking at tension, compression, as well as shear. Now, how do we know when we have designed something effectively? How do we know when our design works? Like your projects, you're looking at the conceptual idea and whether it'll work conceptually, but you haven't actually done any of the stress analysis or functionality analysis or anything like that. You haven't analyzed whether or not physically it'll be able to work. So how do we know when our design will physically be able to function properly? So in your lectures, we have touched on a curve called the stress strain curve. Are you all familiar with this curve? Okay, great. So this is the fundamental of mechanical civil engineering, understanding the stress strain curve. The stress strain curve gives us material properties of materials that we are going to commonly work with. So the stress strain curve is broken down into two regions. We have this first region here, and then this second region. What do the E and P stand for in this diagram? What is this first region? What is this second region? Elastic region, yes, very good. This is the first region. So this is the elastic region. And the second one? Plastic region. Yes, thank you very much, Elizabeth. So this is our elastic and plastic region. And what do these tell us? So let's say we're looking at this member again here. And we're applying some kind of force. And as we apply a force, the stress will increase. The stress in that member will start to increase. In the elastic region, the stress and strain have a directly proportional relationship. So as our stress increases, our strain will increase. It'll remain directly proportional until a certain point. And at that point, the material will no longer be elastic. Okay, it will no longer act like an elastic material, meaning when you take off that load, it won't return to its original shape. Once it reaches a certain point and goes beyond, the material will have deformed permanently. That is called plastic deformation. And that is when the stress exceeds that limit and goes into the plastic region. Now, generally, that is termed as failure. As soon as your part cannot return to its original shape when the load is removed and it is plastically deformed, it is considered a failure because nobody wants to design a part that will change its shape throughout its working lifetime. The limit that we know where a material's properties, or the limit where the material has elastic properties, is called the yield stress. And at this stress, the material will no longer behave elastically. Beyond this stress, it will no longer behave elastically. So we usually design all of our parts, components, machines to have a working stress that is less than or equal to yield stress. So that is how we know if our design is adequate. If our design is able to, or if our design is put under stresses that are less than the yield stress of the material, then we know that our design will work. All right. Now the last question. What is a factor of safety? Any ideas? You can consider this a sort of revision for your shot test. I think shot test next week. what is a factor of safety? Or what is the factor of safety? So a factor of safety is the relationship between our yield stress and our working stress, basically. So the factor of safety is the relationship between our yield stress and our working stress. Generally, we need a factor of safety greater than 1. A factor of safety of 1 means that our yield stress is equal to our working stress. And that is never a good principle to have, because what if we suddenly have some kind of surge in power and there's more load, or there's more forces being generated for some reason, or maybe there is some friction after all, and it generates some kind of heat and causes the part to experience even more force than it needs to. Maybe there's an impact. Maybe too many people stand on something. It has more weight than it's supposed to. That would mean that the part would fail. And that's way too precise. Having a factor of safety of 1, you're not left with any breathing room either side. There's no room for error. So generally, factor of safety can go to 1.2, 1.3, all the way up to 10 and even more, depending on the application. And these factors of safety are industry standards. So for different applications, different industries have different prescribed factors of safety. So for like bridges, you have factor safeties of 3. And then for things which aren't life-threatening, like say this coupling, it may have a factor of safety of just 1.2 or 1.5. All right, not too high. Now, how do we know when, what's stopping us from always designing to a factor of safety of 10? Why shouldn't we just design everything to a factor of safety of 10? That way it'll be 100% never going to fail. Why do we have to do such a low factor of safety for some parts? Why not just design everything to a factor of safety of 10? Any ideas? To not waste materials. Yes, Elizabeth, that's a very good answer. A higher factor of safety means you're using either a lot stronger materials, which are generally more expensive, or you're using more of the material than you normally would. So let's say you're looking at mild steel. If you're going to have a factor of safety of 10, you'd have a really, really big part. Or you could design the part smaller, but use stainless steel, which is also very expensive. And that's just wasting materials and wasting money. So generally, when we design anything, we have 2 things that we have to be able to satisfy. We have to be able to satisfy the safety factor. We have to make sure that our part or our design, whatever it is that we are coming up with, is safe. But then we also have to satisfy our clients, our stakeholders, and make sure that it's cost effective. So we have to find that nice balance between the 2, making sure that a part is safe for the consumer, as well as making sure that it is cost effective for the stakeholders or the manufacturer. Right, now we can look at our assignment. So like I said, if you guys have any specific questions or problems with the assignment, please let me know so that I can focus on those areas. For this tutorial, I will just focus mainly on the hub analysis and the bolt analysis. So, first step is always to do your torque analysis. In your torque analysis, you have the information given in your task brief. Okay, that's fine. No questions there? No questions from the torque analysis? Torque analysis, you're basically given the power and the RPM, and you have to come up with a torque. So once you have that torque, your torque analysis is complete. That's the end goal of your torque analysis. Next step is your key analysis. Okay, we are moving in order of the load path. So the load path is, let's say we're looking at our cross-section of our assembly here. This is part A and part B, shaft A, shaft B. Shaft A is rotating at some torque, and we want to transfer this torque to shaft B to rotate at the same torque. The load path, or the critical load path, are all the parts that join those two bits. So the parts that join them are the shaft, then going to the key, then from the key to the hub, from the hub to the flange, from the flange to the bolt, and then back out the other side. So the order of our analysis will go from finding the torque to the key, to the hub, to the flange, to the bolt. That's why we do it in this order, following the load path. Right. Because the shaft has already been given to us by the client, we don't have to do a shaft analysis. If it wasn't given to us, then we would have done a shaft analysis as well. But as it is, the shaft has been given to us, and the information for the key has also been given to us. The material that they're going to use and the standard, industry standard dimensions for different shafts. Using this information, we have to try and find the key lengths. All right. Now remember, when you find your key length, say your key length comes out to be 50.8 mm. Would you leave your answer like this? Or would you round it off? Round it off. And what value would you round it off to? You could round this off to 51. But let's say you have to give this to a manufacturer. So you tell the manufacturer, okay, we're creating 3,000 units. Okay, like in the question, it says here, the client wants to create 3,000 units. We need to create 3,051 millimeter keys. The manufacturer will have such a headache trying to get that very precise measurement. So it's always good to work in measurements that the manufacturers are readily work with, and they usually work with increments of 5 millimeters. So it's either goes 5, 10, 15, 20, 25, 30. So multiples of 5. So the most appropriate option would be to go 55 millimeters. But you could also go 60 millimeters, or 70, or 75, or 80. But again, you have to come back to the question, am I starting to waste materials? What's my factor of safety? All right. What factor of safety do I want? Where do I draw the line at saying, okay, that's just wasting materials? So for this one, if you round it off to 55, that's probably more, that's probably better than rounding it off to 60, because at 60, you've over-engineered your design by about 20%. Whereas with this one, it's only about 5%. Not 5%, 10%. So this is a little bit over-engineered. 55 is probably the better dimension. So you come out with a key length of 55 millimeters. Now moving on to the hub analysis. All right, so can anybody tell me the type of force that will be exerted on this area? So this is our area. This is our critical area, and we need to find the stress in that area. So first we need to find the force that's acting on that area. So can anybody tell me the type of force that that area will be experiencing? What type of force will be acting on this area? A tensile force. Yes, very good. So if we're looking at a tensile force, so it'll be acting in this direction, pulling that surface. If we're looking at the tensile force, that means we'll be looking at the tensile stress and the tensile strength of the part. Now, for every step, we have to calculate our force. Okay, our force won't be constant, but our torque will be constant. The torque is equal to force times distance. And as we get further away from the center of the shaft, our force will be decreasing because our length is increasing, our distance is increasing. Force and distance have an inversely proportional relationship when the torque is constant. So using this relationship, and since we've already calculated our torque in our torque analysis, and doing just some simple geometry, we'll be able to find our distance from the center of the shaft to the center of the area. We'll be able to find our force. Now for this step here, you have to do some kind of assumption. So our force will be equal to our torque divided by our distance. This distance will be the shaft radius plus half the height of the key plus some assumed distance by you. Now, if you assume that this area thickness is, say, 16 millimeters, all right, you have to do some kind of dummy calculations to find out what is the appropriate thickness. All right, so let's say that you say, okay, I want to assume that this distance is 16 millimeters. So from the center of the shaft to half of that area will be plus 8 millimeters, okay? So your assumed thickness divided by 2. Sum all this up, this will be your distance. Right? And now that we have our force, we can apply our stress equation. So our stress equation is equal to the force divided by the area. Our stress that we're looking at is a tensile stress. Force is tensile force divided by the area. This area is the length of the key multiplied by the height of your hub, yes? So length of key multiplied by height of hub, or hub thickness. Right? Now this stress value we take from the information given to us in the question. So we know that this material being used is cast iron. So we go back to our data sheet and we find the tensile strength of cast iron, which is 8 megapascals. So we use that value and we substitute it here in place of stress. And we try and make the height of the key, height of the hub, or the thickness of the hub, subject to the formula. Come to Ft over stress T times length of key. And we solve for the hub, the height of key, the recommended height of key when the force is this value at our assumed thickness. Now this step is supposed to be iterative. You're supposed to go back and forth, keep doing different calculations for different assumed heights until you sort of narrow in on the most ideal thickness. Now, I can show you very quickly why we do that. Just give me a second. Okay, guys, this session will end in 3 minutes. I will end the session and then restart using, you can join again using the same login information that you did for this session. And I'll continue part 2 of this tutorial. Okay? Okay, set guys. See you in a minute.